All right, well, good morning, everybody. I'll go ahead and flip the recording on, and welcome to another wonderful day of fluids and heat transfer. Today, I'm hoping we'll wrap up our discussion on fluid statics so that next week we can start jumping in and talking a little bit about mass and energy balances and fluids. So, on Wednesday, we started our discussion on fluid statics, and we stated that for any given system, we can calculate the pressure in terms of a reference pressure plus the density of a fluid times gravity times the height of the fluid column of interest, right? So if I've got fluid in a tank at some height h, and if let's say it's a closed tank with some pressurized vessel P naught, and I want to know what's the pressure at the bottom of the tank P naught is simply the density of the fluid times gravity times that height plus whatever the pressure is at the top of the fluid surface. Keeping in mind, this applies to incompressible fluids. And so we worked an example on this. And so let's take a look at another example. So let's say I have a tank now with two fluids, a liquid A and a liquid B. And in these tank, I have two manometers, one at the bottom of the first liquid and one at the bottom of the second liquid. Now, the specific gravity of A is 0.72, and the specific gravity of B is 2.36. And the question is, looking at these manometers, we find that, all right, I'll make A blue. The liquid in the A manometer goes to the top of the column because it's simply A, but for the B liquid, it only goes to a specific height, which is at this point unknown. It's an H. If the liquid B at the bottom goes to a height of 0.3 meters and the top of the liquid A is 2 meters, the question is, what is the height of the liquid B in that second manometer? Well, through application of fluid statics and our understanding of manometers, we can come up with a calculation to determine the height of B. So what we need to know is what's the pressure at the bottom of the tank, which I will call, let's just say P1. Well, P1 is simply the specific gravity of A times a reference density, which in this case, if we're looking at liquids, the reference density is going to be water, which is 1,000 kilograms per cubic meter, times gravity, times this initial height of the liquid, so HA, as well as the height of this liquid B, or HB. So we have HA plus the specific gravity of B, the density of our reference fluid, gravity, and the height of B. Doing this, we look at, well, this is the pressure from the column of A, this is the pressure from liquid B. So putting in our values, we find that the pressure for P1, 0.72, times 1,000 kilograms per cubic meter, times 9.81, meters per second squared times 2 minus 0.3 or 1.7 meters plus 2.36 times 1,000 kilograms per cubic meter times 9.81 meters per second squared times the column height for B, or 0.3 meters. So if we plug that in, let's see what we get. Should be about 18,950 pascals, which is 18.95 kilopascals. So that's the gauge pressure. Because we don't know the pressure at the top of this column, so if we use things in terms of gauge, it doesn't matter. We can get the pressure at the bottom of the liquid column. And so knowing that pressure and that this system is in equilibrium, we can say, well, the pressure in this height as it moves up increases, and at the top of that liquid level, it should be, assuming these are all open to the same container or atmosphere, these should all be the same, which means if this is P naught, this is also P naught, and then the top over here is P naught as well. And so we can say, well, if the pressure here and here are both P1, then we can set up an equation for the pressure as a result of this liquid column to calculate the height. Or I can say 18.95 kilopascals equals the specific gravity of B times our reference density times gravity times our unknown height. So by solving for this, we know that we can figure out the height that would equate in this calculation. Or we get 18.950 pascals over 2.36 divided by 1,000 kilograms per cubic meter divided by gravity, 9.81 meters per second squared. And that should give us our height in meters. Which, doing this calculation, we get about 0.82 meters. And so by application of fluid statics, we're able to determine the height of the liquid B in that second manometer. Any questions on that example? No? Okay. Well, I mentioned earlier that our fluid statics expression only applies to incompressible fluids. So the question is, what happens when we consider a compressible fluid? So what is the issue that arises when we're looking at this expression in terms of vapors and gases?
You wouldn't have a constant density?
The density wouldn't be constant, right? Because as we move through that column of fluid, the density is going to change. And so the anticipated pressure is going to vary as well. So how can we rearrange this expression to correct for the pressure dependence on density? Well, through application of the ideal gas law, knowing that number of moles is mass over molecular weight and density is mass over volume, I can rearrange. That was odd. All right. So I don't know when I cut off for a second, when an internet hiccup. So by application of the ideal gas law and knowing that number of moles is mass over molecular weight and density is mass over volume, I could rearrange this expression and say my density is equal to pressure times molecular weight over RT, and then plug this in here, and then I have pressure is equal to P naught plus P molecular weight over RT times gravity times height. So now I have an expression with pressure on both sides of my expression. Now doing some math manipulation, which I'm just going to wave my math magic wand, I can resolve my original derivative. What I'm left with is an expression that looks something like this. Or this equation may or may not look familiar, but this we call the barometric equation, which accounts for pressure fluctuations via fluid statics and with compressible gases. And one thing I do want to note is a couple things. You'll notice that we have pressure and a reference pressure here. These are the same units, which means everything exponential should be unitless. So when you're doing your calculations, ensure everything that you have within that exponential needs to be unitless. At the same time, there's a negative here within that exponential, which means this negative is when I'll say the negative is valid when you are increasing in elevation with respect to your reference pressure. What that means is if you're starting at sea level and you're moving up, your final pressure should be less than your reference pressure. And vice versa, if you're looking at something that's high up or at sea level and you're moving down, that final pressure should be higher. So just keep that in mind in terms of when it's necessary to use the sign within the exponential term. So let's take a look at an example. So let's say I decided to visit Denver for the weekend. Which has an elevation of 5,280 feet, which is about 1,610 meters, good old Mile High City. My question is, what is the absolute pressure in Denver? So rather than me just jumping in and solving this, I want to give you guys a chance to stretch your mental muscles. So I'm going to shoot you all off into some breakouts and see how well you can all do. So go ahead, and you should be, 4 or 5 of you in a room. See what you guys can do in terms of doing the calculation based off the barometric equation and what's given. Also, I'll say you can assume a temperature of about 60 degrees Fahrenheit, which I think is about 15.6 degrees Celsius. So see what you can do. I'll give you a few minutes and then I'll bring you all back here and we'll discuss. All right, so you should be getting invitations for those breakouts now. And Shay, you're welcome to jump into one and observe, but you really don't have to.
So were you talking to me?
Yes, I said
okay.
you didn't need to jump into a breakout.
Okay.
This also kind of tells me who's paying attention in class and who isn't.
All right, so I got a molecular weight of air of like 28.9. So that'll probably come in handy here.
You can ignore me. I'm a silent observer. But you are right. Molecular weight is 9.
Well, that kind of scared me.
That's good to hear.
Boo. You're all right there, Douglas. All right. Hopefully that was a pleasant experience being flung into the void that is a breakout room. So how did the problem go? As everybody's coming back, did any group come to an answer or a solution
Yeah,
or
we
a,
got an answer.
or a guess? Shot in the dark. I'll even accept those. Partial credit's partial credit, right?
0.83 atmospheres.
All right, I got 0.83 atmospheres. Do I have a second on that?
Second.
All right. That sounds like it should be the answer. So let me flip over and I'll kind of give everybody a rundown for those that weren't able to do the calculation as quickly or had some difficulty. So we have our barometric expression.
Pascals.
There's molecular weight, gravity over RT times H. In this case, H. Now you can do this in terms of SI or English unit. It's really up to you. I know students, most people prefer SI because it's less obnoxious. I apologize, I did not give you the molecular weight of air. It is 29 cabinets per cabinet mole, or whatever unit floats your boat. So for SI, I'll use 8.314 joules per mole Kelvin. The temperature I gave you was about 15.6 Celsius, but we have to use absolute. So it should be 288.6 Kelvin. And I gave you the height. And P naught is 1 atmosphere or 14.7 psi. But the tricky part, or the brunt of the effort, is in determining this exponential. So that's where we're going to focus on. So I have 29. I'm going to use kilograms per kilomole because that's the unit that makes most sense, I guess, even though I really like cabinets per cabinet mole. In 1 kilomole, there is 1,000 moles. And gravity really doesn't change a whole lot in elevation. We're not weird physics majors. Joules per mole Kelvin. T is 288.6, 1,610 meters. And so if you want, you can do a unit check. Kilomoles goes away, moles goes away, Kelvin goes away. And a joule should be approximately kilograms meters per second squared. Meters squared per second squared. So that all cancels. So you run the exponential and you left with P is equal to P naught times 0.83, which if P naught's 1 atmosphere, you get 0.83 atmospheres. So if you ever visit Denver, you'll realize that you're about 17% lacking in atmosphere, which is why altitude sickness is a real thing. Getting some more practice on this. Let's say we decided to continue our trip in the Denver area and we wanted to travel to the lovely Pikes Peak, which if you've never been, I highly encourage it. It's definitely a wonderful view, but Pikes Peak's a little bit higher than Denver with an elevation of approximately, oh, I didn't even share with you the picture. That was rude of me. That's the whole point, was for me to see the picture. It's really fun. It's really pretty. I've been once, but it was cloudy, which kind of kills it. But the elevation of Pikes Peak is about 14,110 feet, which is just a little bit higher. But in meters, that is approximately 4,300 meters. So why don't you all spend I'll shoot you all in breakout rooms, but this time for a shorter amount of time, just to get a little more practice. See what the pressure, the absolute pressure is when we're taking our trip to Pikes Peak.
One question, do we have a temperature?
Oh, that's a good question. Okay, yeah, it's going to be a lot colder up in Pikes Peak. Definitely bring a jacket. So the temperature is probably going to drop to about, I would say, at least 40 degrees, which in Celsius should be, let's say, 4.4 Celsius. Or in the unit that actually matters in this problem, about 277.4 Kelvin. So I'll give you guys just a few more minutes and breakouts to give this a little more practice. You okay there, Carson? Were you able to take attendance, Shay? So how'd it go, everybody?
Good.
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 Getting comfortable with that expression? All right. So were you guys able to come up with a solution and answer?
Yeah.
What'd you guys get?
0.59 atmospheres.
Oof. He is 0.59 atmospheres. Did we have a second group that get that?
Second.
We got as well.
All right. Great job. So yeah, air's feeling a little thin up there. Well, I'm glad you all were able to work through that. One last thing I want to talk about today is the discussion of buoyancy as it applies to Archimedes' law. But I always like to do this via asking questions. So hopefully you guys see the PowerPoint slide. So let's say I have a barrel on a raft, shown here by this wonderful detailed drawing I've done. And the barrel and the raft are floating in a large tank of water. Now, if the barrel rolls off of the raft and into the water, and it floats, does the fluid level increase, decrease, or remain the same when the barrel rolls off and floats in the water? You don't have to answer immediately. I want you to think about it for a few seconds. And then we're going to play everybody's favorite game, rock, paper, scissors. So if you think that the water level increases, you can throw out rock. If you think the water level decreases, you can throw out paper. And if the water level stays the same, you can show me scissors so I get an idea of what your thoughts are. You guys ready? I know this background doesn't do really good with rock, paper, scissors. If you want, I'll turn it off for a second. Let's see. Ready? Rock, paper, scissors, shoot. What do you got? All right, I see some scissors. I see a rock or two. The chat's blowing up. Scissors, rock, scissors, scissors, rock, rock, scissors, scissors, rock, scissors, rock. So nobody likes paper in this. So everyone thinks it either increases or it stays the same. So the answer is, in this case, the fluid level stays the same. So scissors get the point, and rocks, no points to Gryffindor, I'm sorry. All right, the next question. This is the trickier one. Now we're looking at the same situation, but in this case, instead of floating, the raft sinks to the bottom of the tank. Now, do we think the fluid level will increase, decrease, or stay the same? If you think it increases, throw up rock. If you think it decreases, throw up paper. And if you think it stays the same, once again, the tried and true scissors. All right, here you go. Rock, paper, scissors, shoot. What do we got? I got rocks. Stand strong. I like it. Let's see what the chat says. Scissors and rocks again. Rock, rock, rock. A little bit more rock, man. Everybody's a fan of Dwayne Johnson. I appreciate that. He's a pretty good guy. Rock and scissors. I like it. The answer, however, is paper. And that the fluid level must decrease. Now let's take a look as to why. So I like this problem because it's one of those counterintuitive. Most people do not get this. So let's revisit this again. We'll revisit both cases. So first case, I have this situation. Same raft, Now the raft's in the water. So in both instances, both objects float. And Archimedes' law states, and I probably spelled that wrong, so I have to go double check on how I usually spell it right. The weight of an object.
Dr.
Are we
Lopez?
still supposed to be on the PowerPoint?
No, thank you. So it doesn't tell me what I'm sharing, it just tells me that I'm sharing. Do you guys see the?
Now we're good.
The weight of a buoyant force must equal the weight of an object displaced. Or I should say the fluid displaced by the object. What that means is if I have an object or this barrel and it's floating, the weight of that object, which is equal to its mass times gravity, must equal the weight of the fluid displaced by that object, which would equal the volume of water times its density times gravity for that object to float. So if we were going to look at this case on the left here, which I'll call case 1, and I'll call this case 2. For case 1, the weight of both the object and the raft, mass of the barrel plus the mass of the raft times gravity, equals the mass of the water displaced times gravity. In case 2, both objects still float. So this expression still holds. I'll say barrel still floats. For case 3, which was the second discussion, where, or should I draw that? I'll draw case 3 here. We're looking at the situation where the raft floats, but the barrel sinks. The mass of the barrel plus the mass of the raft times gravity is now greater than the mass of the water that's being displaced. Which tells me, since when we do a comparison between case 1 and case 3, the mass of water displaced went from equaling the left-hand side of the equation to being less than the left-hand side of the equation, which tells me that less water was displaced. And because of that, the fluid level fell or decreased. Is that explanation clear, or would you like me to repeat it or repackage it? It's a little odd and definitely counterintuitive. But if you've got it, let's take a look at one final example problem for the day. Now let's say I've got a baseball that's submerged in water. The diameter of the baseball is 3 inches. it weighs approximately 5 ounces. And the question is, what fraction of the baseball is submerged in the water? So we're assuming it floats, because if it sank, the answer would be really easy. So let's think about how we can determine this fraction. Well, we have the diameter, which is 3 inches, or if we want to put it in terms of feet, we can say it's 0.25 feet. And we have, and if you, I'll tell you what will be really nice, and we'll put it all in terms of meters and SI units. So I got 0.076 meters. The weight is in 5 ounces, which is about 0.145 kilograms. So what we can look at, if we're trying to find this fraction, we can look at it in terms of the volume of the baseball submerged. Oh, that crashed. Thanks. Thanks, notes. The volume of the baseball submerged over the total volume of the baseball. All right, well, I think we're actually out of time, and I don't want to go over, just in case anyone else has class after this. Actually, no, this goes to 10:50, right?
Yes.
Okay, I get wires crossed because Tuesday, Thursday ends at 10:45. So that's great. We still have a little bit of time to finish this. So the volume of the baseball is just the volume of a sphere, which, if I remember correctly, should be pi d cubed over 6. Which in this case would be pi times 0.078 meters cubed over 6, which I'm guessing is fairly small. Let's see what I can come up with really. 0.076
I
cubed.
thought the diameter was 0.076, not 78.
0.076, is that what I, oh, I apologize, thank you. 0.076. So if I take 0.076 and I cube it times pi divided by 6, I get something really small, 2.3 times 10 to the 4 cubic meters, which I'm not surprised, it's a baseball. So then the question is, well, what's the volume of the baseball submerged? Well, we stated that by Archimedes' law, the mass of the baseball times gravity has to equal the mass of the water times gravity that's being displaced by the baseball. So if we get rid of that, we can say that the volume of the baseball.
Can I ask something real quick?
Yes.
I thought for the volume of the sphere it was pi d cubed over 8, not 6.
It's 6.
Okay.
So we know the mass of the baseball. So what we can do is find the volume that would be displaced of the water, which would tell us the volume of baseball submerged, which would indicate that that volume would be simply the mass of the baseball times the density of water. So the mass we had was about 0.145 kilograms. The density of water is 1,000 kilograms per cubic meter, which in this case should give us a solution because of 1.45 times 10 to the minus 4 cubic meters. And so that fraction is 1.45 times 10 to the minus 4 cubic meters over 2.3 times 10 to the minus 4 cubic meters. Which should give you a solution of about 0.63 or 63% submerged. All right. Any questions on that example problem or the discussion that I had of buoyancy? If not, then that's all I have for today. And that about wraps up our discussion on fluid mechanics. So thank you guys all for your attention, as well as working with me to have an excellent first week. Next week, we will get into the fun stuff of mass and energy balances in fluids. That's where the good stuff begins. So I'm excited. And as always, if you have questions or issue on homeworks, feel free to jump into the office hours with me here in a second or send me an email. Don't forget, it is due tonight at midnight in terms of that first synthesis assignment and homework assignment. And quiz 1 will be due Sunday at midnight. Is there any last minute questions? Yes.
It's a question just about like our quizzes. So I know you said that our tests are open notes and things like that, but are our quizzes the same way?
Yeah, I can't police that. So
Okay.
yeah.
Just wanted to verify before taking the quiz for Sunday.
Oh no, you're fine. I get that.
Thank you.
You're welcome. Any other questions? All right. If not, have a great day, everyone, and have a great weekend.
Thank you.
Thank you,
Bye,
Dr.
thank
Lopez.
you.
Thank you.
Bye.